It's loading. I don't know what it does behind the scenes, but setting up for YouTube Live. We're good.
You're good?
Yeah.
Okay. Okay, then I think we should start. Thank you everyone for joining us for the first EPSP Connect seminar of the season. As you all know, the purpose of this series is to bring the community together and to help establish connections between people who might not be able to interact with others in a different setting. So we are really happy to have you here. And I would like to thank all the team members who helped plan and organize this series, who reach out to potential speakers, coordinate with them, advertise in social media, and make sure that the series information is up to date on the website. As we have done before, the format of the science talk is same. Please post your questions in the chat as they come. Um, you don't need to wait till the very end, and Roberto and I will monitor them. At the end of the talk, if you prefer, we are also able to ask you to unmute and you can ask the question directly. For those of you who are listening to our live stream on YouTube, we will also keep an eye on it for the questions. For the talk today, we have Professor Chelsea Scott and Dr. Cassandra Brigham from the Open Topography team with us today, and we are very happy to host them. Chelsea Scott is an assistant research professor at Arizona State University and a remote sensing specialist with Open Topography. Her research focuses on topographic change analysis and seismic hazard to critical infrastructure. Cassandra Brigham is a postdoctoral researcher at Arizona State University, and she's a research scientist at Open Topography. Her work brings together geomorphology, geospatial AI, and geostatistics to better understand how Earth's surface evolves and how we measure it. So without any more delay, Professor Scott and Dr. Brigham, please take it away.
Thank you very much for the introduction and the invitation to speak here today. Cassie and I are very happy to tell you about our work for Open Topography and specifically topographic differencing. Since there's two of us, if you have questions during our presentation, certainly feel free to put them in the chat and we can answer them. We've prepared to talk about 45 minutes, and so we'll have some time left over at the end as well. So to begin, here is the outline of our presentation. We will begin by introducing Open Topography, and then we will discuss topographic differencing, followed by error in differencing, which has been a lot of the work that we've been working on for the past few years. And then we'll be looking at an interesting case study of applying differencing to the 2025 fires in Los Angeles. And then we'll conclude by discussing our work to overcome some challenges in implementing on-demand and large-scale topographic differencing within Open Topography. And to get you going, on the right, you can see a picture of two topographic hillshades. These were acquired at different times in the portion of Salt Lake City. And then the red, white to blue image is the topographic change. And you see all of those blue squares. And so those are new houses that were built between the acquisition of the two LiDAR data sets. And so today we'll be diving into looking at more examples of topographic change and how we can work to understand these results. But to begin with, what is Open Topography? So Open Topography's goal is to democratize access to high-resolution topography data. So essentially make it easy for you to access and then use topographic data in whatever your research application is. We are an NSF-funded data facility, and we are within the Geoinformatics program within EAR. And you're welcome to check out our webpage at opentopography.org. So here is a picture of the OpenTopography team. There's 8 of us, and we are at collectively the San Diego Supercomputer Center, which is part of the University of California, San Diego, the EarthScope Consortium, and Arizona State University. The bulk of our infrastructure, specifically the supercomputers, are at San Diego Supercomputer Center. So if you've ever run a job on OpenTopography, you're turning on and using the computers in San Diego. And OpenTopography was founded in 2009, and we've been growing ever since then. And I'm really excited about what we've been building over the past decade and a half. So in more detail, what do we do? So we host and distribute topographic data, and specifically LiDAR and global topography data sets. And so you can come to OpenTopography and download these data sets. Since these data sets can also be challenging to use, we have created on-demand processing tools so that you can generate topographic derivatives such as digital elevation models, topographic hillshades, slope contours, and we also have on-demand topographic differencing. There's different ways to access our data, which can be useful for people looking for different amounts of data or with different programming skills. So you can access data via the OpenTopography portal, via API, and via different notebooks, so essentially programmatically. And OpenTopography has been heavily involved in education and training, often focusing on training graduate students to use topography data in their graduate research and beyond. And we have an annual webinar series, often in the spring, so look at it if you're interested in that. And then short courses, and all of the material generated from this is on our website. So OpenTopography has a large community and impact. We have been, or 260,000 people have registered on OpenTopography to access our jobs, or access our data sets. There's over 141 users of the API. And we have a monthly newsletter that goes out to 68,000 people. And for the most recent proposal that we submitted to the NSF, we wanted to quantify the impact of OpenTopography within the academic community. So this plot on the lower right shows the percentage of use of OpenTopography versus institution by Carnegie classification. And so not shockingly, we are used most at R1 or very high doctoral research activity institutions. But OpenTopography is also used at a variety of other institution types. And the number above each of these bars indicates the number of institutions where someone has accessed topography data from OpenTopography. So for example, we've been used at 98 different associate degree granting institutions. And so again, we're very proud of this broad use of OpenTopography among different types of academic institutions. So now we're going to get into the bulk of our presentation, which is focused on topographic differencing. So we hope, Cassie and I hope by the end of today to present it or to convince you that topographic differencing is a really powerful technique to measure change to the Earth's landscape. We can look at natural as well as anthropogenic processes like erosion and deposition along rivers, earthquakes, landslides, and urban development. And so topographic differencing really gives us a way to image how these processes change the Earth's landscape, and then ultimately to better understand the underlying processes that lead to natural hazards. But we found that calculating topographic change and then understanding the uncertainty is challenging. So for the past 5 or so years, OpenTopography has been working to make a variety of topographic differencing tools more standardized and easier for the community to use. The left image here is looking at a critical zone observatory in South Carolina, and we can see the changes in vegetation and the landscape between the different LiDAR acquisitions. And these data sets were collected to understand how the land recovers following extensive agricultural and water degradation. So we'll now discuss the 2 primary types of topographic differencing. First, starting with vertical differencing. So to do differencing, we need at least 2 different data sets acquired at different times. So here we see we have a topographic point cloud. So that's 3D XYZ points. And here we have the pre-event data set, so before whatever event is a focus, and in the literature, sometimes called the compare. And then we have the post or the reference. And you note here that there's a lot more pink points in the post data set than blue points in the pre. And that's because the LiDAR data quality increases over time. And so we're going to have better quality with lower error and higher point density over time. So the next step in the differencing is to take these 2 point clouds and grid them to identical grids, so the same bounding box and the same resolution for both data sets. And we can then do a raster subtraction, which at some level is quite simple. And this is taking the reference and then subtracting the compare. And we use the color scale that's shown here, where red indicates downward motion of the Earth's surface, for example, due to erosion or a landslide. And then blue indicates upward motion of the Earth's surface, for example, from deposition. And here's an example of looking at topographic change at Yosemite National Park between 2006 and 2010. And in this area, we can see the rock falls in this area, and then also the associated loss of vegetation above these rocks. And these 2 data sets were collected specifically for looking at and measuring where and the amplitude of these rock falls in Yosemite National Park. The other common type of differencing is 3D topographic differencing. And these are differencing results shown for the 2016 magnitude 7 Kumamoto earthquake in Japan. And each of these arrows represents the 3D displacement. The arrows is the horizontal displacement, and then the color is the vertical. And that pink ellipse is the uncertainty in the topographic differencing results. So these look a lot like GPS displacements. And in some ways, they are similar in that they're 3D, but they are much more spatially dense than GPS displacements. So they really give us an opportunity to look at that full 3D deformation field, often at the tens of meters resolution. And the 3D differencing is done with the iterative closest point, or sometimes abbreviated ICP algorithm. And that's done by taking a windowed subset of the pre and post-event topographic data. And the 2 point clouds are then aligned using a rotation and translation. So there you can see that the blue point cloud is iteratively moved towards the red point cloud. And it's that entire deformation that is the assumed 3D deformation of that area during the earthquake, for example. All right, and now I will turn it over to Cassie.
All right. So as Chelsea, here we go. As Chelsea talked about, we have this increasing availability of LiDAR data sets. And that's really revolutionized our ability to measure landscape change. But as we want to detect smaller changes, like centimeter scale changes, understanding uncertainty starts becoming critical since the error in our measurements can be the same magnitude as the real changes we're trying to detect. And traditional approaches like thresholding miss the spatial structure of errors. And so when we do try to sum up change over an area, we start to sum up the biases of our results. And so that's why I'm going to argue that we need a more sophisticated geostatistical approach. But first, let's take a look at the types of errors that we see. So I'm going to show an example from Columbus, Indiana, where we have two LiDAR data sets, one from 2011 and then one from 2017. So here are the different vertical differencing results taken from two digital surface models. So that includes points from trees, buildings, etc. And then from two digital terrain models. So that is just the ground return, the two models from the ground return. And so what is being shown here is not just the actual difference between the two areas, it's the actual difference plus the error. And I'll show you a couple examples of that. So the actual difference is the changes in vegetation between these two time periods, any erosion, uplift or subsidence, construction and excavation are major changes that we can see, or horizontal translations from fault motions. So in the DSM, we can see an area where buildings have gone up in the between the two time periods. We can look at the vegetation along a river, and so we can see areas of new plantings in blue. In the areas where you see kind of a motley red and blue area, that's where you see where leaves have come on and off. So these might have been taken during different seasons. On the DTM, in areas of construction, you can also see that the ground surface has come up as well. So you have fill areas in areas of construction. You can also see anthropomorphic activity resulting from agriculture activity. So here in the adjacent fields. And then let's take a look at contributions from some of the error. So you'll notice if you look closely along the river, you'll see these patchy triangular sections. And this isn't true change. So these come from interpolation errors that where points are kind of either misdiagnosed or the interpolation algorithm it doesn't take care of them correctly. You can also see if you look closely at some of the buildings in the DSM, you'll notice that one side of the building shows uplift and the other shows subsidence. And so this is indicating that there is kind of this horizontal shift here to the left. On the DTM, you can see very faint traces on the DSM, but it's very obvious on the DTM. You notice this kind of characteristic banding. So this isn't true change. The land hasn't scrunched up in a wave-like form. These come from LiDAR aircraft banding. And so we'll talk a little bit more about the flight striping later on. And we have more examples of point misclassifications and interpolation errors. And here, this data set doesn't contain bathymetry, but points were misclassified as being part of the river. And so in the older data set, and so it shows that all areas of the river have been experiencing subsidence when this is not actually the case. So before we delve too deep into the the parts of the error. We have to remember that error in LiDAR and in many areas has a spatial structure. And so just to get you used to looking at some of these patterns, I've generated some examples of what these patterns would look like. So on the left, we have an example of spatially uncorrelated, kind of a spatially uncorrelated raster. And spatial, the correlation range length increases as we go to the right. And so here on the left, it's correlated at the length scale of 2 pixels all the way up to 50 pixels on the right. So we categorize LiDAR differencing errors into 3 spatial scales. At the short scale, so meters to tens of meters, we see random noise, point misclassification, and geometric distortion on steep slopes. At the mid scale, so hundreds of meters, we encounter horizontal alignment errors and flight line striping. At the long scale, so kilometers, we deal with vertical datum issues and systematic calibration errors. Each scale requires different approaches for detection and quantification. So let's look a little bit more closely at each of these error sources. So this is a particularly egregious example of vertical differencing results from a data set with incorrect metadata. So this type of error manifests as apparent vertical change across our data set with systematic changes ranging from a few centimeters stemming from an incorrect geoid, so using, for example, geoid 12B instead of geoid 18. And it can go up to tens of meters as the example here. This is an example from Eastern Washington. And that stems from the confusion between ellipsoidal and orthometric heights. So elevations are recorded relative to a reference ellipsoid, and sometimes it's useful to know an elevation relative to a geoid. So that's the hypothetical ocean surface. The height to the surface above the geoid is termed orthometric height. And so if you get the orthometric height confused with the ellipsoidal height during metadata recording, that's when you get these large mistakes. But writing down the wrong geoid will still give you smaller mistakes on a long range on the order of tens of centimeters. Airborne LiDAR surveys are typically conducted along multiple parallel and overlapping paths or flight lines. And another common error type we encounter in topographic differencing is the presence of stripes resulting from alignment errors. These are essentially georeferencing errors that create linear swath-to-swath artifacts aligned with the flight direction. They're typically on the order of tens of centimeters or less vertically. The resulting stripes don't represent real topographic change. The width of the swaths range between hundreds of meters to kilometers. And these errors are particularly problematic because they can interfere and distort our understanding of linear features like roads or faults on the surface. And they're really a pain to correct. So now we're going into kind of our mid-scale errors. So accurate vertical differencing results require that the topography data sets are well aligned, or in other words, are correctly georeferenced. So when horizontal georeferencing errors are present, a topographic feature in one data set is offset from itself in the other data set. So this is shown in the schematic example where our brown profile T1 is our pre-event compare profile, and the green profile T2 is our post-event reference profile, where the topographic peak is mapped at different locations in the pre and post-event dataset due to a georeferencing error. The differencing results show apparent vertical deformation that correlates with the direction of the topographic slope, so like the buildings that we saw earlier in the Indiana example. In the schematic example, the left side of the peak shows apparent subsidence or erosion, and the right side shows apparent uplift or deposition. Now getting to our short range error, differencing digital terrain models show the shape of the bare earth and how that changes over time. accurately generating them requires that the LiDAR point cloud data are correctly classified to differentiate ground points from other features such as buildings and vegetations. Sometimes the ground is incorrectly or inconsistently classified, and that leads to different models of the ground surface. And this can be true around buildings where there are no ground points to constrain the DTM. So in the lower left corner, you can see an example of point misclassification from a building. And so they're often characterized by kind of these triangular features. And then finally, there's geometric distortion. So when the angle at which the LiDAR sensor intersects the ground surface is far from perpendicular, it can lead to greater horizontal displacement errors for each point in the data set. So the geometric distortion affects the precision of the elevation data, making it more challenging to accurately measure changes in topography. And this is particularly true for areas with steep slope or very complex terrain, as you can see in the example from the Grand Canyon on the left here. And so you see that these bands of high difference are correlated with the areas of high slope. So now that we've cataloged some of the types of errors present, let's think about how we go about quantifying their effect on vertical differencing results. So for very long range errors, that is errors that are almost perfectly correlated at the scale of like an area of interest that we'd be looking at, we are interested in a vertical bias, that is a vertical alignment error that should be close to constant across our area of interest. For spatially correlated errors at the long, mid, and short scales, error magnitudes will change across the raster at different rates. So we want to quantify the mean uncertainty across the raster that error types at each spatial scale introduce. To do that, we can model short scale, mid scale, and long scale correlation patterns of the differencing results. We can also account for uncorrelated random error at a very short range, but computing the mean uncorrelated uncertainty across the area of interest. We can propagate the mean correlated uncertainties computed for each of the correlation length scales and the mean uncorrelated uncertainty into a total mean uncertainty, which gives us two measures of error. So this vertical bias and a total mean uncertainty. So we're going to look at these error parameters within this example. So this is an example from Minnesota. And you can see flight line striping as kind of the principal source of error. So we're pretending our area of interest is the entire raster. And by taking the median of all of our differencing values, we can get a vertical bias measurement. And that is kind of our estimate of our very long range error. But to get at our mean correlated uncertainty, we are going to employ a tool called a variogram. So variograms are tools that are used in geostatistics to explore spatial relationships between data points and how those change over distance. So it's defined by the variance of the difference between data values at two locations plotted as a function of the distance between those locations. So I'm going to go over a very quick primer about how you would go about constructing a variogram. So let's say you have a raster of differencing values. So again, red means subsidence or kind of going down, and blue means going up. So you're going to sample your raster. Here we're sampling every point in our raster. Our variogram calculation that we have for our workflow is optimized for performance and accuracy. And we sample at a density that balances computational efficiency with statistical reliability. And so let's take a look at a calculation for a single point. So you're going to look at the points at a certain lag distance, at a certain distance h, towards all the points there. And you're going to calculate the variance at that lag distance for all of the points from that single point. And that'll give you a semi-variance value for that lag, for that single point. And then you would do it for every single point that you sample. And then you would go ahead and increase the lag distance and calculate your variance for those points, and so on. And so like that, you get a measure of the variance as you go along. And we then model the variogram. Here we use up to three spherical models. Variogram models are characterized by a range. So again, that's that characteristic correlation length, and a CIL, which is the maximum variance. Just going back to our variance, our error patterns. Here are what the variograms would look like of each of these characteristic error patterns. So if you had completely random error, your variogram would be flat at the CIL. So the CIL is equal to the value of that. At 2 pixels, you're going to reach your CIL at range 2. That's going to be your characteristic correlation length. For your 10 pixels, you reach it, your range is equal to 10. And then obviously 50 pixels, your range is equal to 50. And so here are for spherical models. So this, for our Minnesota example, this is what its semi-variogram looks like. And so you can see that it has 2 characteristic correlation lengths, one at 22 meters, which corresponds to a lot of the road features, so the offsets, the slight horizontal shifts caused by the roads and the streams. And then we have a very distinct correlation length at about 1 kilometer, and that is that's indicating the correlation length of these flight line stripings. And you'll notice in the variogram that there's an oscillation, and that oscillation also is indicative of this flight line striping. So how do you take that to an uncertainty value? So we take the parameters of the modeled variogram and convert that to covariance values. And then we integrate over our area of interest to get that our uncertainty value. And so you have to select your area of interest beforehand in order to get an averaged uncertainty value. So I'll talk about that in just a second. And then we compute our uncorrelated uncertainty, and we report it as a differencing value plus or minus your uncertainty value for each of your polygons of interest. So this is a crucial concept. Uncertainty isn't a single number, but it depends on the scale of the analysis. So a landslide deposit might have a very different uncertainty than the entire hill slope. Our tool calculates mean uncertainty for the area, but these graphs show you kind of how things might scale. So it's supposed to help users understand whether they can detect changes in their specific features of interest. The decay rate will depend on the correlation range and the CIL from the variogram. Generally, uncertainty decreases with the aggregation area, so with your area of interest. So you'll have, if you have a very large area, you'll have much smaller uncertainties because you're averaging out your uncertainties over these larger areas. If you have a smaller area, you'll have higher uncertainties. And the rate at which those uncertainties increase will depend on the CIL and range of your modeled variogram. So it's important to tailor your error analysis to your area of interest. So just as a reminder, we calculate our vertical bias as the median of all of our differencing values. We calculate our correlated uncertainty from variogram model parameters, And we do a Monte Carlo integration over our area of interest to get at an averaged uncertainty value. We get our uncorrelated uncertainty to represent random noise. And then we add those two in quadrature to get our total mean uncertainty. So let's take a look at a case study where we implement this. So the Eden fire kind of provides a good test case for our methodology. So this was a devastating wildfire that burned through terrain in Los Angeles County in January 2025. So it burned 57 square kilometers. There were 17 fatalities and over 9,000 structures that were lost. We got access soon afterwards to post-fire LiDAR from NV5. We only had access at that time to the DTM. So one of our plans soon is to redo our analyses with the point cloud data, which we will have access to soon. And one of the questions we had was whether we could quantify dry arrival sediment delivery to headwater channels. The problems that we were dealing with is that there were multiple error sources in all the sources of data. So the post-fire LiDAR was also for kind of uncorrected first data that was out. It was very heterogeneous terrain, and what we were looking for were pretty subtle signals. So our initial analysis, our initial differencing revealed problems. So we can see three distinct correlation scales in our variogram. The 25-meter scale likely reflects real small-scale processes or local errors. The 1800-meter scale suggests flight line issues, but that 337-meter component is diagnostic of horizontal misalignment, which we can easily see in the hill slopes. Notice how it correlates with the aspect wherever you look. So this tells us we need to co-register the data sets before proceeding. But it'll allow us to test if we co-register the data sets and that 337-meter component disappears, that our tool is accurately tracking the components. And it does. So once we co-register the data sets, we are still seeing those two correlation scales at 22 meters and at about approximately 2 kilometers. But the correlation scale at the 300 meters, so that kind of hill slope correlation length, is gone. So we also noticed that the overall magnitude of the semi-variance, so the overall magnitude of the total error in the area has dropped as well. So now let's focus on a small area in the hillside and see if we can get some calculations there. So we measured 4 channels. So we measured the kind of delivering hill slope and then the channel itself. All 4 channels show statistically significant aggregation, so 20 to 30 centimeters of deposition, and those exceeded our uncertainty bounds by more than 10 centimeters. And so this confirms dry arrival sediment delivery, or this confirmed that the headwater channels were receiving sediment post-fire. However, the hill slope erosion signals of just a few centimeters fall well within our uncertainty envelope. So you can't validate that these erosion signals are coming from specifically these hill slopes with confidence. But it illustrates the importance of the rigorous uncertainty analysis. It tells us what we can and cannot detect. So we've made our uncertainty workflow accessible through 2 pathways. So for quick analysis and to quickly get the parameters of interest, the OpenTopography platform provides on-demand processing with just a checkbox. We're going to be implementing a version soon, which will allow you to select your area of interest so you can actually get area-specific uncertainty values, hopefully in the next month or 2. For advanced users who want that right away, our Jupyter Notebook offers full control over the analysis. So that includes the ability to define stable areas and analyze specific features. So both versions are open source and freely available. The cloud implementation democratizes access to the sophisticated error analysis, and the Jupyter Notebook allows you to really make it your own. All right, I'm going to hand it back over to Chelsea now.
You can hear me? See my screen? Perfect, thank you. All right, so at OpenTopography, we were then motivated by the fact that differencing of high-resolution LiDAR topography is possible over about a quarter of the US's lower 48. So this provides a really interesting opportunity to look at change from a variety of natural and anthropogenic processes. But this also brought the question of how to move from that site scale that Cassie and I have shown you already today to a larger scale and to do so systematically. So we looked at two activities. One is the on-demand topographic differencing. And Cassie told you about the second part of that, which is the implementation of the error code. And then also we've done statewide topographic differencing for the full state of Indiana to look at really how you move to quite a large scale for differencing. So the first activity was to add on-demand topographic differencing onto OpenTopography. And our goal was that in just a few mouse clicks, users can run vertical and 3D differencing along with an error calculation. And we were motivated to standardize a differencing approach and ultimately wrote a peer-reviewed publication on the approach that we implemented in OpenTopography. We wanted to democratize access to the differencing tools, and we wanted our workflow to solve common but very challenging issues, such as coordinate reference system projections that must be done before any differencing activity. And we, of course, encountered several challenges along the way. So the algorithm had to work with legacy, so older data, and hybrid data, so differencing LiDAR with structure for motion derived topography data sets. And the data also had to work with future data sets without being changed frequently. The algorithms had to work on demand, so essentially they could never fail. And they could never fail along with no real input from the user. And the algorithms had to work with the cyber infrastructure and high performance computing resources that back OpenTopography. So we ultimately implemented topographic differencing, which you can see here for the White Sand National Monument in New Mexico. This is on the left, you can see the topographic hillshade. And if you look at the shape of those dunes, you can see or hypothesize of the direction of the dune propagation. So you see this is an example of wind coming from the southwest towards the northeast, and the dunes are then growing in or migrating towards the northeast. And on demand on OpenTopography, you can do vertical differencing, and that's shown in that middle plot with the red, white to blue color scale. And the blue represents an increase in elevation, and that's on the northeast side of the dunes. And so this indicates motion towards the northeast. And on the right, you can see 3D differencing. 3D differencing generally assumes that the landscape maintains its shape and just shifts. And that's not quite what's happening in the dunes, but they generally do maintain their shape. And with some noise, we do see that those arrows point towards the northeast, again, showing that northeastward motion. And if you're interested in implementing these on OpenTopography, you can go and select a region of overlapping data. And when you do that, you'll find this differencing tool button is available. And if you click that, that will then take you to options of doing vertical and or 3D differencing. And if you're looking to do Cassie's error tool, look for in vertical differencing, look for this option number 3, error handling. And then you'll need to select, just put a box in that first section, estimate mean uncertainty using geostatistical approach. And then the OpenTopography will compute that full uncertainty analysis. And building on this work, we were then interested in figuring out what we need to go from that site scale, which you can do on OpenTopography portal, to big scale. So we looked at doing LiDAR differencing, so meter scale differencing for the full state of Indiana. And so again, we're motivated by what does large scale topographic differencing look like, particularly looking at changes over roughly a decade, which is the separation between these statewide data sets in Indiana. And we're interested in looking at the computational and technical challenges required in this large scale data processing. We often get asked the question, well, why did you pick Indiana? So it's, I believe, still the only state in the US with 2 full statewide data sets. So really, it was the only option. And second, we anticipated a lot of interesting change due to the variety of anthropogenic, fluvial, and Great Lakes landscapes in the state of Indiana. And third, OpenTopography has been in a data hosting partnership with the state of Indiana, and we're looking at growing that partnership. So this is big data. The processing was about 2 to 3 orders of magnitude larger than past differencing studies. And this really forced us to really think about the computational components between or underlying the differencing algorithm. And one of the, I think, most interesting examples of the differencing is looking at sinkholes. And this is in southern central Indiana. At the top, you can see the topographic hillshade. We get this sort of golf ball imprinting on the landscape. And then the bottom plot shows the topographic differencing, where those red circles represent sinkholes that formed between the 2 LiDAR acquisitions, and blue represents sinkholes that were filled in between those acquisitions. So here are the results for the statewide differencing for all of Indiana. On the left, you can see the digital terrain model. So this is the terrain with the vegetation removed. And the most prominent thing that you see are probably those north-south and east-west flight line errors. But if you zoom in, you can see a lot more. For example, patterns along the rivers that cross the state of Indiana, as well as lots of quarries and mines, particularly in the southern part of the state. The middle plot is looking at the digital surface model. So this includes the vegetation. And here we see quite significant signals along the rivers, from those rivers and their surrounding riparian zones. And we also see significant changes in vegetation, for example, from purple here to red here. And these represent seasonal differences in when the data sets were acquired. And you can check this browsable map here, portal.opentopography.org/Indiana. And that's a GeoServer where you can browse around and see the topographic change for all of Indiana. So to conclude, I'll just be reviewing OpenTopography's resources. So we have an OpenTopography differencing page, which is linked there. And this includes a lot of material that we've built over the years looking at topographic differencing, so including examples and blog posts, video tutorials, and then code available from GitHub. And here are two peer-reviewed publications that we've discussed. The first is in Geosphere, looking at the on-demand topographic differencing tools. And the second is Remote Sensing, looking at statewide differencing for Indiana. And so here are the conclusions for our presentation. Hopefully today, Cassie and I have convinced you that topographic differencing is a powerful technique for measuring changes to the Earth's landscape. There is significant error in LiDAR differencing results, and this error is spatially structured and scale dependent. And our uncertainty analysis captures multi-scale patterns and includes automated tools that makes this challenging analysis accessible. And applying this uncertainty allows or supports making more confident interpretations of differencing results. And finally, OpenTopography has worked to democratize access to topographic differencing tools along with the error calculation. And so thank you all for coming today and listening to our presentation. You can learn more about OpenTopography there on our website. And you're welcome to contact us at info@opentopography.org. And that, if you email that, will come to me, as well as a few other team members. And we welcome you to follow us on our various social media platforms. So thank you.
Thank you.
All right, thank you. There's been a few questions that came through the chat, and I think most of them have been given an answer. However, since this is also being recorded and it's going to live in YouTube, I think it might be good for some of those to be answered live, even if just briefly. So I'm going to start with the first one that popped up. It was, does OpenTopography have tools to calculate uncertainty, like the semi-variogram?
So yes, I linked those, or do you want to do it, Cassie?
Oh, yeah, no. Yeah, so we have links to we have a Jupyter notebook that runs you through our area, and then there's also the Python source code with those tools. And you can run the Jupyter notebook also on Colab if you don't want to set up the environment.
Can people find the links to your GitHub through the OpenTopography website?
Yes.
Okay.
Chelsea, if you wanted to share the web page for the vertical differencing web page.
Yeah, so I put on, that top page includes all of our resources. In the link, the opentopography.org/learn/differencing.
And under code, you'll be able to find the code there.
And then we also taught, or Cassie taught, a short course at Sage Gauge there, which has a little bit more material as well.
All right, what I'll try to do is copy these links and post them on the YouTube description. So if you're watching this video, go down there to the description and you'll find the links that have been shared.
All right, I think we have a second question, which is, I think, on the first example of error analysis that you presented, Cassie. How do you observe a second range at 337 meter? And how do you know that it is simply a longer oscillation as shown in one of the previous examples? Good.
Yeah, so I think this is kind of a question of like what threshold at which do you add? Do we add another model to our kind of combination of models that we use to model this variogram, and kind of how aleatory is this? And so the algorithm kind of automatically tests a very kind of long list of models, and those include Hole effect models, which kind of account for oscillations. So it takes into account that there are potential oscillations at various scales, and we use various criteria to select kind of the best model with the simplest parameters. And so we're looking for kind of as simple of a model as we can that still models it as best as possible. And so if it chooses to have three models and one of those parameters is included, we deem it important enough. But of course, it's not perfect. Model selection rarely is. So it's possible that you're picking up on something sometimes that is not actually that significant. But I think in this case, there's also a, a good physical explanation for that 300 correlation length scale and what that is corresponding to. So it's that kind of hillside scale error that we're seeing in that area.
So the next question I'll link to, one is, can we import data that has been collected with, people's uncrewed aerial systems to those tools, or does it need to be hosted first through OpenTopography? And then I'll link that to one that came later saying, is there any reason why these tools would not work with bathymetric data with multi-beam? So people interested in using this for potentially rivers, estuaries, bathymetry.
Yeah, so as long as you have a good understanding of the potential error sources and their length scales, I think that's really important for the interpretation part of things. There's no reason you can't use a kind of a geostatistical approach to characterizing these errors. So I think that would absolutely work on multi-beam data. The actual like interpretation as to like what the error source is based on the length scale is going to be different than kind of pure ground-based LiDAR. And so that requires like the extra step, but the processes behind it, yeah.
Then there is a question about how error and uncertainty are handled when differencing data sets derived from different point cloud resolutions. So for example, if point clouds of different densities are resampled to the same resolution, does the lower resolution product introduce a systematic bias? And then I think it would scale with surface roughness. And can we correct for this?
Yeah, so that happens very often because older data sets often have much lower point resolutions than younger data sets. And so whenever you're differencing anything pre 2015, it's going to be at a much lower resolution. And so that has, in my observation, that has mainly kind of lended itself to like interpolation errors, misclassification errors, and then also geometric distortion errors in high slope areas. So these are all kind of small scale errors that accumulate over areas. And so kind of um, the geostatistical approach kind of encompasses that, and we model them as small scale errors.
And to add a tiny bit to that, it's better to if you're picking a resolution for the differencing, the lower density data set should guide that. So if the lower density is 1 point per square meter, it does not make sense to grid the data to half a point per, or to 50 centimeters resolution, no matter how good that second data set is. And I also, to answer the question from earlier, so if you would like to apply this to your own data set, then the Jupyter Notebook and/or Collabs option is definitely what you should be using. If you're interested in seeing your data on OpenTopography, I linked to the community data space where we'll take modest-sized data sets, essentially collected for academic use, largely by the US scientists. And so you can see those data on OpenTopography. However, we do not have the differencing tools applied to those data sets.
All right, and I guess we'll take this as the last question. We're at the top of the hour. Does the uncertainty calculation also work for multitemporal data, such as deformation velocity generated from INSAR time series?
Yeah, so that's an interesting question, and I've started kind of talks with Catherine Guns and Sarah Minson at the USGS to see how applying kind of these geostatistical approaches could work for INSAR. And again, I think we have to be careful in the interpretation, and I think it's less straightforward than, say, applying it to multi-beam data. But that's definitely something we're working on right now.
All right, I think we have reached the time limit we had. So thank you so much again, Dr. Scott and Dr. Begum. And thank you for all the attendees for joining us today. We have EPSP talks lined up for the next month, so we'll keep you posted on our page and also send an emails out. Yeah, thank you so much for joining us today, and see you for the next
Thank you
talk.
so much, Shashank.
Thank you for the
Thanks.
invitation.